In this video, I am going to show you how to use the calculus versions of the rotational kinematics. So here are the formulas. The first formula is for instantaneous angular velocity, so that's omega equals the first derivative of the angular displacement as a function of time. The instantaneous angular acceleration, that's alpha, is equal to the first derivative of the angular velocity as a function of time, which would be the same thing as the second derivative of the angular displacement as a function of time. Oh, and there should be a 2 up there. And then the change in angular position is the integral of the angular velocity. And the change in angular velocity is the integral of the angular acceleration. So let's do a couple of sample problems. During a certain period of time, the angular position of a swinging door is described by theta equals 5 plus 10t plus 2t squared, where theta is in radians and t is in seconds. Determine the angular position, angular speed, and angular acceleration of the door at A, t equals 0, and B, 3 seconds. So let's start by just taking the first and second derivative of our angular displacement function. That way we have an expression for angular speed and angular acceleration. So the angular velocity is equal to the first derivative of the angular displacement, which is going to equal the derivative of this expression here. So the derivative of 5 is 0, the derivative of 10t is 10, and the derivative of 2t squared, use the power rule, so it's 2 times 2, and then t, so plus 4t. That's our expression for angular speed. And then our angular acceleration is going to be the first derivative of angular speed. So the derivative of 10 is just equal to 0, and the derivative of 4t is equal to 4. So it's just 4 radians per second squared. Okay, so for part A, we want to find theta, omega, and alpha at 3 seconds. So we're going to do theta equals 5 plus 10 times 0 plus 2 times 0 squared. Those terms will just go away because they're 0. So theta at 3 seconds, or sorry, at 0 seconds is just going to equal 5 radians. And circle that. And for omega, it's going to equal 10 plus 4, plug in our 0, and then it's just 10, so 10 radians per second at 0 seconds for the angular speed. And then our alpha is just 4 radians per second squared the entire time. And then for part B, we want to do the same thing, but at 3 seconds. So our angular position is going to be 5 plus 10 times 3 plus 2 times 3 squared, which ends up equaling 53 radians. So circle that. And then our omega is going to equal 10 plus 4 times 3, which ends up equaling 22. And the correct units there are radians per second. And then our alpha is the same the whole time, our angular acceleration. So it's just 4 radians per second squared. So just doing a little bit of calculus there and plugging in some numbers. Our second sample problem involves some integration. So we have the angular acceleration of a wheel is alpha equals 6t to the fourth minus 4t squared, with alpha in radians per second squared and t in seconds. At time t equals 0, the wheel has an angular velocity of 2 radians per second and an angular position of 1 radian. We want an expression for the angular velocity and the angular position as functions of time. So for part A, we want to find omega, and omega is going to be the integral of the angular acceleration as a function of time. So let's integrate that. And just some basic use of the power rule. So this is going to become t to the fifth, and we need to make sure that the 5's cancel, so we'll need a 5 on the bottom, so it's going to end up equaling 6/5 t to the fifth. And then here with the power rule, this is going to become a 3, and we need a 3 on the bottom here to make sure it would cancel out when taking the derivative. So it's going to be minus 4/3 t to the third. Then we want to do a definite integral here, so we're going to say plus c. Now, the problem tells us that at t equals 0, the wheel has an angular velocity of 2 radians per second. So what we're going to say is we're going to plug in 0 here and 0 here, and then that will equal 2. So that'll go away, and then that'll go away. So we know that c is equal to 2. So our full expression for angular velocity is omega equals 6/5 t to the fifth minus 4/3 t to the third plus 2. And that is our expression for angular velocity. Now, we want to take the integral of our angular velocity in order to get our expression for angular position. So taking the integral of this here, it's going to end up being t to the sixth, and we want a 6 on the bottom here to cancel, make sure it cancels out. So we're going to have something that looks like that, but those two 6's will cancel, so it'll end up being 1/5 times t to the sixth. And it's going to be a similar thing happening here with this 4/3 t to the third. This 3 here and t cubed is going to become a 4. So it would be but we want those 4's would end up canceling, so it's going to end up being minus 1/3 t to the fourth. And then that's going to become a plus 2t. And we want a definite integral here, so it's going to be plus c. And it tells us that at t equals 0, it has an angular position of 1 radian. So if we set theta equal to 0, so plug in 0 there, plug in 0 there, or sorry, if we set t equals 0, then our theta is going to equal 1. So in this case, c is going to equal 1. So our full expression for angular position as a function of time sorry about that, 1/5 t to the sixth minus 1/3 t to the fourth plus 2t plus 1. So hopefully you know how to use rotational kinematics within the context of calculus now.